We are studying in this video about the various factor of operating variables. So we are studying about fuel air ratio here. So in this point we will study this parameter, that is maximum pressure. The pressure of a gas in a given space depends on its temperature and number of molecules. The curve P3 therefore follows T3, but because of the increasing number of molecules, P3 does not start to decrease until the mixture is somewhat richer than that of maximum T3. So fuel air ratio is 0.083 or air fuel ratio is 12:1, which is slightly richer because stoichiometric air fuel ratio is 14.6:1. So it means about 20% rich. You can see in this diagram here, on this side you have P3 pressure, on this side we have a mixture strength expressed as a percentage of stoichiometric mixture. So this is your compression ratio 10, 8, 6, 4. It is sure that if your compression ratio increase, your higher pressure will increase, because compression ratio is directly related to the pressure. Higher is the compression ratio, higher will be the pressure at P3. You can see here this curve is will follow is increasing. The higher pressure will increase. Take this example at R is equal to 10. The pressure is increasing as your stoichiometric it tends to towards stoichiometric mixture, and it will increasing, and up to this point this is 120%, means 20% richer mixture, your pressure will increase, and after this your pressure will start to decrease. So it means it follow the same curve as temperature, except one thing, that is it will start to decrease at a 20% mixture, while temperatures start to decrease at 6% rich mixture and above that. The exhaust gas temperature T4 is maximum at the chemically correct mixture as shown in this figure. At this point the fuel and oxygen are completely used up, as the effect of chemical equilibrium is not significant. At lean mixture, because of less fuel, T3 is less and hence T4 is less. If temperature T3 is less, definitely T4 is less, because whatever the maximum temperature achieved after combustion, then your gases will expand, and the same at the exhaust will be affected. At rich mixture, less sensible energy is developed, and hence T4 is less. That is, T4 varies with fuel air ratio in the same manner as T3, except that maximum T4 is at the chemically correct air fuel ratio in the place of slightly richer fuel air ratio 6%, as in the case of T3. However, the behavior of T4 with compression ratio is different from that of T3, as shown in the figure 3.13. You can see here in this figure, this is your temperature T4, and this on this side you have percentage of theoretical fuel. So this is your stoichiometric mixture. You can see the exhaust temperature is less at the lean mixture. If you use a lean mixture, your exhaust temperature is less, and if you use a stoichiometric mixture, your exhaust temperature start to increase, and after stoichiometric mixture, because of dissociation and other factors, and your exhaust temperature start to decrease. You can see here the exhaust gas temperature T4 is lower at high compression ratios. You can see when the compression ratio is high 10, your exhaust temperature is low, and when your compression ratio is 4, your exhaust temperature is high. Basically, you can understand by this example that if we want compress the gas, if you start burning fuel in open environment without any engine, okay, you will get only temperature, you won't get any pressure, you won't get any power output. Take the example of a burning of fuel outside in a, you can say, open space. If you burn the fuel, you will get only temperature, there is only no pressure, and you won't get any power. But if you burn that fuel in an enclosed chamber, in a engine, in a closed chamber, then you will get some pressure. Okay, so same here, you can see when your compression ratio is 4, your temperature is higher. So this does not make any sense for us. This is not desirable. We need pressure also at the same time, because we want power out from the engine. The piston will be moved by high pressure gases. Piston can't be moved by only temperature. You understand my point? you can say it, you can take the example of a high pressure gas only, like pneumatic conveying system, or you can say a pneumatic gun, where only high pressure gas is required to do the work. What I'm saying is the temperature does not make any sense. We don't need temperature, we need pressure also. So when your pressure ratio is 4, your temperature, exhaust temperature is high, which is none of any use to us, which is wastage of energy. So when R is 10, your temperature T4 is less, so means higher compression is desirable. You can say unlike T3, the exhaust gas temperature T4 is lower at high compression ratios, because the increased expansion causes the gas to do more work on the piston, leaving less heat to be rejected at the end of stroke. So this point is important, because the increased expansion causes the gas to do more work on the piston, leaving less heat to be rejected at the end of stroke. The same effect is present in the case of air standard analysis also. So next is the mean effective pressure increases with compression ratio. It follows the trend of P3 and P4, and hence it is maximum at a fuel ratio slightly richer than the chemically correct ratio, as shown in figure 3.14. Shows a summary of conditions which give maximum pressure and temperature in a constant volume cycle, assuming fuel air cycle approximation. You can see in this figure, this is percentage of theoretical fuel and this is mean effective pressure. As this is the lean mixture here, your lean mixture, you will have this much amount of mean effective pressure. As your mixture starts to become stoichiometric, your mean effective pressure will increase, and as your mixture will become at this point 120, which is the richer mixture, you will get the maximum mean effective pressure, and further your percentage of theoretical fuel increase, the mean effective will start to decrease. So this is at compression ratio 4, and the same curve will be nearly for compression ratio 6 and 8 and 10. So it means you can clearly see that if you increase the compression ratio, your mean effective pressure will be more in the higher compression ratio. This above analysis is combined here. You can see here variable maximum, at what point it will be maximum, this parameter, and what is the reason. So first is temperature T3, which we know temperature after heat depletion. So it to maximum temperature T3 is a 6% rich mixture. It means 14:1, and the reason is because of chemical equilibrium, some oxygen is still present even at chemically correct fuel air ratio. More fuel can be burned. Limit is reached at 6%. If greater than 6%, rich carbon monoxide formation. If the mixture is rich, it means we had less air to burn, and we will get partial combustion products, that is carbon monoxide. The next is your pressure P3. P3 is the maximum pressure after the combustion. So the maximum pressure is when you have 20% rich mixture. It means 12:1 air fuel mixture. So as you know from here, PV, reason for this is PV pressure depends on N, R and T. So pressure depends is a function of temperature and N. So it means when temperature is maximum and when number of moles are maximum, then pressure will be maximum. So that we will get at 12:1 mixture for the maximum pressure. The second is temperature at exhaust. So maximum temperature we will get at chemically correct fuel air ratio. So no effect of chemical equilibrium due to low temperature and incomplete combustion at rich mixture. So this is the reason. The next is your mean effective pressure. We will get maximum mean effective pressure at 6% rich. It means air fuel ratio is 13.5 ratio 1, and mean effective pressure follows the trend of P3 and P4. So this is up to here, the different variables and their effect on the performance of the engine, and subscribe this channel, and if you have any doubt you can comment in the below blocks, and for more videos you can give suggestion. Thanks.